I'm Bill Farmer. Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. We are working on the topic of simple type theory, and today we're going to talk about the semantics of core Alonzo. So we're going to define the semantics for a language of Alonzo. So our language is right here. This is our language. We're going to assume we have this language. We're going to define the semantics for that language. So the first thing we're going to do is define a frame for the language. And a frame will be a domain, a non-empty domain, for every type of the language. So it's a domain for every type of the language. And there's some conditions here. The first is that the domain for Omicron, which is the domain for Boolean values, will be false and true. And then the domain for function types, for the function type, let's say alpha, arrow, beta, it's going to be the set of some total and partial functions from the domain for alpha to the domain for beta. And this domain does not have to include all functions, but it includes total as well as partial functions. Now notice we did not say anything about a domain for a base type. That's because there's base types, domains for base types are unspecified, except they have to be non-empty. Okay, now a frame is full is if all the domains for the function types include all functions. Not just some, but all functions. Now an interpretation of L, it's going to be a pair where we have a frame and an interpretation function, and that function maps each constant in C of type alpha to an element of the domain for alpha. And then if we take these domains for the base types and the interpretations of our constants in C, that defines a structure. The next thing we need to define is an assignment into our frame. Now assignment is just a function phi whose domain is a set of variables of L. So phi takes a variable and its value would be some member of the domain of alpha if the variable is of type alpha. And just in first order logic we have this way of taking phi and adjusting it. So we change what phi does on x of type alpha. It will go to d, where d is some value in our domain for alpha. And otherwise, phi stays the same. And then we're going to define, if we have an interpretation, missing a parenthesis here, an interpretation of L, we'll let assign M be the set of all assignments into the frame of M. Okay, so now we're ready to define the really important definition, the definition of a general model. So let us say we have a frame and we have M as an interpretation. So we're going to say that M, this interpretation, is a general model if there is a partial binary valuation function, v superscript m, such that for all assignments phi, and all expressions c of L, either the valuation function gives c a value in d sub gamma, c is of type gamma, or it is undefined. it gives C no value whatsoever, and each of the following conditions are satisfied. Now, one thing, notice that this is a binary function. So we normally would write this like this, but we don't. We write it like this. In a slightly more compact form. Okay, so these conditions basically give the semantics of each of our 5 kinds of expressions. So I'm going to go through each of these. The first says that the value of a variable is whatever phi says the value of the variable is. And a value of a constant is what I says the value of the constant is. And the value of a equality is true if the value of A is defined, the value of B is defined, and these two values are equal. Otherwise, the value is false. So in particular, if the value of A or the value of B is undefined, the value of the equality is false. Now, the value of a function application is simply the value of the function applied to the value of the argument. If the value of function is defined, the value of argument is defined, and the function is defined at the argument. Otherwise, the value of the function application is false if beta equals omicron. So if the value of this normally would be a truth value, then it's going to be false. Otherwise, it's undefined. And finally, the value of a lambda expression, a function abstraction, it's going to be a total and partial function f, such that for each d in the domain alpha, so this variable is ranging over the domain alpha, the value of f at d is going to be the value of b, where we have just phi, so that the value of the variable x goes to d. And it has this value if the value of b is defined, and otherwise fd is undefined. I should say it's undefined if the value of b is undefined. So if we go back and look a little bit at what's going on here, variables are always given a value, constants are always given a value, and equalities are always given a value. And function abstractions are always given a value, though the value could be a partial function. The only place where we can have values that are undefined is here. And it can occur if f is undefined, a is defined, or f is not defined at a. And so this is why the valuation function is partial. In terms of function applications, the valuation function may not give any value at all. Now there's a proposition, general models exist. We said that when we started, M was an interpretation. Right here we said M was an interpretation of L. Now interpretations do not have to be full, but if it is full, we can define by induction. We can define by, or we can prove by, I should say, we can define by induction that such an M would be a general model. Now let's talk about standard models. So if M is an interpretation of L, we'll say M is a standard model for L if D is full. And it turns out every standard model for L is a general model for L. Now, script D being full just means that all the function domains include all possible functions. So for a general model, in order for an interpretation to be a general model, there have to be enough functions in our domains so that when we assign values, like we assign values here or values here, these values must exist in our interpretation. If they don't, we won't be able to have a general model. Okay, so that's what a standard model is. And we'll say a general model is a non-standard model if it is not a standard model. So this means that the logic or the language of Coralonzo has two semantics, one based on general models and one's based on standard models. And normally when people think about the semantics of simple type theory or even higher logic, they think of it in terms of standard models. But we'll see that in many ways it's convenient also to think of the semantics in terms of general models. And when we think of the semantics in terms of general models, we have a semantics which is very much like first-order semantics. When we think of it as with standard models, it's like higher-order logic semantics. Okay, so now we can define the notions of satisfiability, validity, and logic and semantic consequence. And these definitions are very similar to what they would be in first-order logic. So I'll quickly go through them. So phi satisfies a formula in M, which we write like this. If V assigns to A the value true with phi as our assignment. So that's phi satisfies A and M. A is satisfiable in M if this is the case for some phi, and we say A is valid in M, or we can also say that M is a model for A, which we write like this. Notice we drop this. If this is true for all assignments phi, and if B is a closed formula, we say B is true or false in M if the value assigned to A is true or false. So if our formula is closed, we can talk about it being true or false in M. Otherwise, we have to talk about it being satisfied or valid, satisfiable or valid. And now we say that A is valid in the general sense, which we write like this. If every general model, if M satisfies A, or I should say if A is valid in M, or M is a model for A, for all general models, and then we have something similar for standard models. A is valid in the standard sense, which we write like I wrote right here, if M is a model for A for all standard models for L. Okay, so we have a few more definitions. So now let's look at the definitions when gamma is a set of formulas. Phi satisfies gamma M, which we write like this. If there's an assignment that satisfies A in M for all A in gamma. And we can say gamma is satisfiable if this holds for all, it's satisfiable if this holds for some general model and some phi. And then M is a model for L, which we write like this, if M is a model for every formula A in gamma. Now here's a very important definition. This definition is the definition of semantic consequence of gamma in the general sense or standard sense. The definitions are very similar. So A is a semantic consequence of gamma in the general sense, which we write like this. If gamma is satisfiable, I should say if phi satisfies gamma in M, implies phi satisfies A in M for all general models for L and all phi assignments. And the other definition is A is a semantic consequence of gamma in the standard sense, which we write like this. If phi satisfies gamma in M, implies phi satisfies A in M for all standard models M and all phi that are assignments into M. Okay, now this is a little bit complicated because this definition allows gamma to include free variables. If we restrict gamma, if we restrict the formulas in gamma to be closed formulas, so that's what we assume for delta. Delta is a set of closed formulas. Then we can say that A is a semantic consequence of gamma in the general sense, if and only if every general model for, this should be, sorry, this should not be U, this should be delta. Every general model for delta is a model for A, and A is a semantic consequence of gamma in the standard sense if every standard model for delta is a model for A. So we get, so this lemma gives us a special case of semantic consequence. It's a bit simpler, and basically just to repeat, something that is a semantic consequence means, so if A is a semantic consequence of delta, it means that A will be valid in every model of delta. Okay, so we're going to stop here, and next time we're going to talk about how we can define operators in core Alonzo, operators like Boolean operators, the quantifiers, and some defineness operators. So we'll stop here. Thank you very much.